Alright, so with this I'm just going to go over a quick couple of things on comparative statics. The first thing is defining the kinds of problems we're interested in. Not sure why that decided to autocorrect. There we go. These sorts of problems. And we're going to talk about the unconstrained problems right now, but recall that you can turn constrained problems into unconstrained problems through the use of a Lagrangian. There's some more nuance between the connection of those two things, but for this we're going to talk about unconstrained problems. So if we define a optimization problem as some function that deals with a parameter, and I'm going to talk about the single parameter case, but this can easily be extended if you just consider multiple parameters and you look at one of them at a time. So we're going to define the value function v as this actual solution to the problem you get once you've found the maximum value. So whereas x star is the optimal value, you plug that back into your function, and that's what you get for this value function. So there are two main questions that we concern ourselves with in comparative statics. The first one, how does v change as the parameter changes? And how does the optimal choice variable change? And I guess, yeah, for our purposes, I'm going to just do this in one choice variable, but again, it could be easily extended when you just look at one of them at a time. But anyway, so how does x star, the optimal choice variable, change as that parameter changes? And to be precise, there we go. So there's our motivation. So there are two ways we can go about looking at solving these problems. The first one is probably one of the lamer options, is compute it directly. So you could figure out what x star is by solving the first order conditions. Then you could put x star into f. Then you could differentiate f of x star with respect to theta. And that's how you can answer this first question. If you wanted to answer the second question directly, you could compute x star from the first order condition as a function of theta, and then take its derivative with respect to theta and see how it changes. Now both of those ways require a little bit of work. So there are two very common shortcuts. For this one, the envelope theorem. For this one, supermodularity. So the envelope theorem says the derivative of v with respect to theta is equal to the derivative of f with respect to theta evaluated at the optimal x value. And so with this one, all we have to do is optimize it and find x star, and then differentiate the objective function and put x star into that result. Now, this may not seem very much easier at the very beginning when you're just looking at this, but it is quite a bit easier in practice. You might get some wacky expression for x star, and then you have to put that into f, which could give you another wackier expression, and then differentiate that whole thing, which is not a very fun thing to do. Whereas this guy, you take one derivative at a time. You don't have to take something complicated, put it into something, and then differentiate it. So in practice, this tends to be a very helpful result. One of the very common applications of this from this class is the Otelling's lemma one, where define profit as I think this is how we defined it earlier. And if we want to find the partial derivative of pi, profit, with respect to p, the envelope theorem tells us we can just differentiate the objective function with respect to p. And so we get just f of x evaluated at the optimal x. So just that function here evaluated at whatever our optimal x turns out to be. And you can solve that pretty simply with first order conditions. That's just one application of how you would answer this question using the shortcut. Now to talk about supermodularity, the big result here is if f of x and theta is supermodular, then the optimal choice increases as theta increases. And that's pretty helpful because then you don't have to compute anything. You don't actually have to compute x star as a function of theta and differentiate it. You can just do this and see what happens. You can see if it's supermodular. So, the simpler way to prove supermodularity, if you can swing it, is to do this. If this is positive, supermodular. Sometimes that derivative might not exist. Sometimes it might be very annoying to compute. In that case, you would have to use the actual definition. If for any basically we're going to pick x and x prime, theta and theta prime with these relationships. Just two parameter choices and two variable choices. This has to hold for any of them. This side can be interpreted as the difference between f of x prime and f of x holding theta at the bigger parameter value. This side can be thought of the same thing at the lower theta. And so if you can show that this is true for any x and x prime, you win. And the way that you can prove that is by assuming that this is the case and then seeing if you can show this to be true. And that sometimes requires working backwards by starting with this inequality and working yourself backwards, but make sure it flows both directions or you might do some kind of error that would look like this one. Let's see, let's try, 1 equals 2 is obviously false, but you can multiply both sides by 0 and get 0 equals 0, which is true. But that does not mean this is true. So that's why I say you have to be able to work it in both directions. This works, this one does not. So make sure it works in both directions. So that's what I'll say on that. And again, the analog for submodularity. Submodular decreases this goes the other way. That's how you extend it to submodularity. And then you could also talk about very similar ideas for minimization problems. But again, there's just nuance and stuff in that can be talked to death, but this is kind of the big idea of how you would handle these sorts of problems. And I think he has in his notes and stuff, like the reference sheet, these kinds of things. I think he might also have them in some of the stuff in the file section. Other than that, supermodularity stuff is stuff that you can Google and find resources on. I'm pretty pressed for time at the moment, and I want to get these out so that it's actually useful for the exam in the morning. But yeah, there's more that can be said on that. And one other thing I want to touch on, because somebody requested it. I haven't looked up if that's how you spell Stackelberg or if it's L-E. Forgive me for that, I don't remember. Now, I'm not going to go through too much on this, but the main idea of this one is analyzing a sequential game, and the way that you solve for that is you have the two people. I'm just going to talk about this generally. You have two people. Person 1 chooses. Person 2 sees this choice, and they choose. So person 1 doesn't have the information that person 2 does when they make their choice. Person 2 knows what the other guy is going to do and gets to best respond. Person 1 doesn't get that luxury. So you can think about it kind of that way. In Stackelberg competition, you can analyze who is better off from this and all sorts of things. You can analyze if there's a first mover or a second mover advantage, and Stackelberg competition is one example of this, where you can break it down that way. But the main idea with how to solve problems like these is to use something similar to backwards induction. What we did kind of in the more discrete case when there were just a few outcomes is person 1 chooses, person 2 chooses. What you would do is you would work backwards. You would start here and you would say, okay, person 2 would choose this branch. So we kind of erase the other branch. Person 2 would choose this branch. So we erase the other branch. And then you backwards induct and go, okay, now faced with these being person 2's choices, what is person 1 going to do in the choices that they have left? Are they going to pick this branch or this one? They might pick this one, and that's what you would call like the subgame perfect equilibrium thing. And that's something you talked about a lot in class. It's a very similar idea. What you do is you first look at person 2. They pick their thing, their response, seeing what person 1 picked. And then person 1, in that remaining choice, now x2 is going to have a function of x1. It basically is going to depend on what the other guy does. Then person 1 solves this. They solve their problem by backwards inducting on what person 2 is going to choose to do depending on what they do. And a kind of intuition for this is to think person 1 is thinking, if I do this, I think they're going to respond with this. And that's kind of how you can interpret this. There's a lot more that can be said on that, but Stackelberg competition is one of those things that is kind of decently Googleable, and plus I'm pretty short on time, but I did want to kind of touch on supermodularity and Stackelberg competition. I do hope this is helpful, and best of luck on y'all's exams, or I guess at this point, exam. Yeah, it's been a fun semester. Have a